Hello, I want to talk about an interesting reaction that's an application of some of the addition elimination chemistry that we've been talking about recently. The name of this reaction is the Wolff-Kishner reaction, and it's a reaction that enables you to take a carbonyl and turn it into an alkane. So this is a very curious reaction, right? So the carbonyl turns into a CH2, which is a little bit bizarre and kind of unexpected based on the reagents that we have. Often it's written out this way. It's useful to know what the other products of this reaction are as you think about what the mechanism might be. So the other products of this reaction is we're going to generate two equivalents of water and we're going to generate N2, so nitrogen gas. And so it's important to know that. Another key point as you think about this is that there's a key intermediate, and that intermediate is this. Right? And that thing is called a hydrazone. For us, it really just looks like an imine, right? And so I think knowing that that's the key intermediate, that can help us as we think about what the mechanism of this reaction might be, right? Because I would expect us to be able to figure out how to get from the ketone to that imine type intermediate based on chemistry that we've already talked about. I think it's a little bit more challenging to get from that key intermediate to the final product, right? And so what I want to do is just write out the entire mechanism so that you can see how this whole thing goes. Now the interesting thing for the conditions, right, we have hydrazine, which is NH2, NH2. We have potassium hydroxide, so we're under basic conditions. Under basic conditions, we're not going to have positively charged intermediates. We're going to have negative and neutral intermediates, right? So this is the difference, a key difference in this mechanism versus stuff that we've already seen, right? So we're under basic conditions. So it's important to note that, all right? We're used to when we do these reactions, protonating things, having positively charged intermediates. That's not going to be the case in this reaction because we're under basic conditions. And also just to note that the uppercase delta is our symbol for heat. So when you do this reaction, you throw in everything and then you heat it up to get it to work. All right, so since we don't have acid, we're not going to protonate with the first step. Okay, so in the first step, we're just going to have the hydrazine nucleophile, which is a good nucleophile, is going to add to the carbonyl. It's going to give us our tetrahedral intermediate. We're going to do a proton transfer. And so that gets us to this neutral tetrahedral intermediate, right? The reaction is going to continue to go because these tetrahedral intermediates are not stable. You can have a leaving group on them. And so you can have, since we're in basic conditions, you can have hydroxide leave. Right? And again, this may be a flaw in my mechanism because now I have that positively charged intermediate that I told you not to get to, but that'll quickly be deprotonated and it'll give you the key intermediate that we mentioned before. Okay, so we formed our key intermediate. And again, all of this should look a lot like the chemistry that we've done to make imines and enamines and acetals and ketals and those sorts of things, right? And so the interesting question then is, how do we get from this key intermediate all the way up to the alkane, to cyclohexane? And that's where things get really fascinating. And so let's give it a shot, right? So, and again, I would expect you to be able to come up with a reasonable mechanism to here. From here, it gets a little bit crazy, and I wouldn't expect you to be able to come up with this on your own. Now we're going to start using hydroxide. Right? Hydroxide is going to start deprotonating stuff, so we're going to pull off a proton there. get a negative charge. One thing that's helpful as we think about the mechanism is we know we need to get to nitrogen gas, so we need to get N triple bond N. So we can draw a resonance structure that's going to get us closer to there. Puts a negative charge on carbon, right? And again, these are resonance structures, right? So make sure we have the right arrow. And that's going to enable us to react with water to make the first CH bond that we need. And then we just do that again. OH minus is going to pull off another NH bond. So that's going to give us that molecule. And from there, we can generate nitrogen gas. And we leave behind C minus, which is a really unusual leaving group, and it's very unstable. So why is it reasonable to make that leaving group? Well, we've got a lot of heat. You can do things that are not easy to do normally if you have heat, so heat's helping us out. Also generating nitrogen gas, incredibly stable. And this is a completely irreversible step. You can't bring the nitrogen back in. So with heat, it's possible to break that bond. And then in the final step, we're going to use water again to protonate and make that second CH bond, right? So again, this final part of the mechanism is one that I would not expect you to be able to do on your own. Again, the first part, getting to the key intermediate, that's something that we should be able to do. The only difference from stuff we've done before is we're doing it under basic conditions instead of under acidic conditions. But again, it should look a lot like things that we've done before.